I go by Tiffany.
Tiffany.
And you may begin.
Okay.
And please start by introducing your mentor, your departmental mentor.
So, hello everyone. My mentor is Dr. Tal Socek, and he's a faculty in mechanical engineer, and I'm a student in the chemical engineer. So today I'm here to present my research on direct measurement of colloid stability using atomic force microscope. First, I would like to begin with a little introduction of my research topic. So a colloid is a suspension of insoluble solid particle in a liquid medium. It is widely used in materials that have applications in medicine, environment, as well as next generation materials. One of the important properties that we study about colloid is the colloid stability. Colloid stability impinges on many aspects of scientific significance. Some that come to mind include dispersion, emulsion, and suspension in pharmaceutical materials, the formulation of paint, as well as some water clarification in water residues. So the colloid stability depends primarily on two kinds of interactions. One interaction is the van der Waals dispersion force, and it happens when uncharged particles fluctuate with each other, and it is responsible for an unstable colloid. Another interaction depends on the electrostatic interaction, which is when charged particles repel each other. So, according to the DLVO theory, if we can determine which kind of force is dominating at a particular moment in a colloid system, we will be able to determine its stability. One of the important ways to measure colloid stability is by zeta potential. Zeta potential is a numerical value that indicates the degree of resistance between particles. On this slide, you can see zeta potential's value is closely related to colloid stability. If we have zeta potential less than 10 microvolts, we have an unstable colloid. While if we have greater than 50 microvolts, we will have a stable colloid. Now the question is, how do we determine zeta potential? Currently, zeta potential cannot be directly measured. We usually use methods, theoretical models such as electrophoresis, to determine zeta potential. Electrophoresis is when we're applying electric field through a colloid mixture, and the particles in a colloid will migrate to the electrode that have opposite charge with the particle, and it migrates with a velocity that's proportional to the magnitude of zeta potential. However, the method of electrophoresis is both complex and also it doesn't really give us exact value of zeta potential. So the purpose of our research is through using a novel atomic force microscope-based technique to measure construct a complete intermolecular potential between individual colloid surfaces. With the intermolecular potential, we will be able to directly measure the zeta potential as well as other important colloid properties. So here's the image of what interaction potential will look like, and that is a kind of image of how we set up our experiment. So now let me introduce the methodology. So when we're setting up the experiment, we're fixing a silica particle of approximately 5 micrometer of diameter to a cantilever tip. We're using the cantilever tip throughout our experiment to keep our spring constant to be 0.03 newtons per meter. Before each experiment, we need to clean the silica glass surface as well as the glass surface the silica bead is in contact with. We clean it with methanol, isopropyl alcohol, and acetone in order to remove any potential organic waste. Also, we blow dry the glass surface and the silica bead with nitrogen just to clean it thoroughly. Then we insert the cantilever and glass surface into the atomic force microscope. and then we take a force measurement. The solution we are using is made of water and hydrochloric acid with controlled pH. So after we have set up our experiment, we're ready to measure the force curve. We need to start several hundred nanometers above the surface and slowly approach the glass surface. Also, we need to set the deflection sampling rate to be as high as possible. Currently, we're using 50 kilohertz or higher. That's the maximum we can achieve using the AFM that we have. So the reason we're doing that is because we want to obtain as many data points as we can at any separation distance. So here's an example of a force distance curve we have for a glass surface at pH 7. The red line is the extension line. That's when the cantilever is approaching the surface, and the blue line is when we're retracting the cantilever. But in this experiment, we're primarily focusing on the red extension line, because that's when we can see how the cantilever is fluctuating with the thermal noise and how it is behaving when it is approaching the glass surface. Okay, so here comes the most important part of our research. After we have our force distance curve, we're ready to do a Brownian force reconstruction method to construct the intermolecular potential. And this is cited from the past, This is cited from the past research, and it is measuring how the protein is behaving in solution. And we think it is very useful in our experiment as well. So first we take our force curve on top of that, and then we break it into small sections. Each section contains 20,000 points. Then we plot all the data points in each section into a histogram to calculate the cantilever deflection probability density. With the histogram, then we use the Boltzmann's distribution equation to convert the cantilever deflection probability density into relative energy. And we do that with each section, and we combine them into a complete intermolecular potential profile. We can also obtain force curve, the very accurate force curve that describes the colloid behavior by taking the derivative of the energy profile. So here's the Boltzmann's distribution equation. It is very important. It helps us to relate the potential energy at any separation distance related to the position the cantilever is in and its probability distribution function. So here's our results. This is my results. This is a force curve at silica surface at pH 4. The top one is what we have from atomic force microscope, and it gives us the cantilever deflection versus the tip sample distance. And on the bottom is our intermolecular potential profile. And because of the massive amount of calculation we need for each force curve, because we have, let's say, millions of data points for each AFM curve, we need to incorporate all the calculations, the Boltzmann distribution equation, as well as the Brownian force reconstruction into a MATLAB code. So we can just put in the AFM data into the MATLAB code, and it will return as a complete intermolecular profile. And to calculate the zeta potential using this profile, we need to calculate the divide length at each pH, or say salt concentration, and find the corresponding energy at this curve to this divide length we have, and then we can get our zeta potential. If we want to see our data of zeta potential is accurate and correct, we need to compare that to past experiments, let's say electrophoresis data. However, we have developed another test to test if our result is valid. So here's the graph. It's the intermolecular profile for 3 pHs from pH 7 to pH 3. And we can see the adhesion of pH 3 is much greater than pH 7. By the way, the pH 3 adhesion is the blue line, and the pH 7 profile is the red line. So there are a great amount of adhesion at pH 3, and that can be explained because the silica particle has an isoelectric point at pH 3. So at pH 3, the surface is in neutral charge, which means we will have more van der Waals dispersion force at pH 3. Therefore, there are greater amount of adhesion. And also zeta potential at pH 3 is the greatest among the 3 pHs, and that is validated by past experiments. So using our method, we prove that our research data is generally true. So in conclusion, our novel atomic force microscope-based technique measures the interaction potential profile directly and help us understand material properties under many different conditions. And our research is very important in determining zeta potential as well as other properties. All the past experiments have not returned us a very accurate, let's say, like a very accurate intermolecular potential because they're not able to eliminate other thermal noise or Brownian motion. So here's a reference of some papers I used. And I need to give special thanks to my advisor, Dr. Tal Sawchek, and graduate students who helped me, Dan Potter and Lynn Fan. And thank you all for listening. I'll be happy to take any questions you have.